Alright, well, welcome back. So we've been talking about binary search trees and recursive algorithms for working with trees, searching, deleting, inserting, traversing in particular. Recursion, we talked about stacks a few lectures ago, and I mentioned that stacks were used to keep track of information when you make function calls. And recursion is really all about, calling yourself, which requires you to keep track of where you were, because if you just jump to the top of a function, you need new copies of your local variables, and when you're done and you return, you need to remember what the old values of those variables were. So a lot of housekeeping, and stacks work really well for that. Stacks work well for a lot of other algorithms that aren't directly related to what we do with binary search trees, but are actually fairly similar. So I want to talk about a few applications of stacks with respect to some other algorithms and some general approaches to solving problems, and then look at how we can use a stack to do traversal of a binary tree without using recursion, so we can kind of do what recursion is doing for us, but do it manually in a loop. And then I want to talk briefly about queues and how queues can be used for some algorithms, including for traversing trees. So we're thinking about stacks and queues with respect to algorithms, and there's a general notion of depth first versus breadth first. Depth meaning move deeper and deeper into a tree, and if you think about our kind of general tree traversal algorithms, if you start from the root, you keep moving down further and further into the tree, and play around at the deepest parts of the tree and jump up a little and come back down and so on. And in an in-order traversal, we do all this stuff on the left side before we ever get to the root, right? We traverse the entire left subtree and then we print the root value. So we're going down deep into the tree before we come back up and print the root node and then start exploring the right. That's a depth first notion. But there's also something called breadth first, and in a breadth first approach, we would start from the root and we'd explore all of its immediate children, and then after we had visited those, we would explore their children. We would slowly be moving deeper and deeper into the tree. So let's see what this has to do with algorithms in general, and I want to begin with the idea of running a maze. And so here's an example of a maze, and let's just suppose that we're trying to start from this opening and we want to finish at this opening, and we're looking for a path. So most people have tried doing this, and the general method is, you start off, and when you have a choice in different ways you can go, you just make a choice. Maybe you say, okay, I'm going to go straight instead of going left. And then I'll come up here, and here's another place where I can go left or right. I'll try going left. I hit a dead end. Okay, what do we do at that point? We go back to the last place we made a choice, and we say, okay, instead of going left, maybe I should go right. And we go right, and we hit another dead end. And so now we back up and we say, okay, I made all the possible choices I could have from here. Let's go to the previous choice. The previous choice was right here. I chose to go this way, and that didn't work out. Let me choose to go left. And so we'll go left, and we'll come over here and start following this. And now we get to this point, and there's another choice to be made. Should we go this way or that way? And maybe we say, okay, well, let's try going this way first. So we'll come down here and we'll start exploring, and we'll come over here, and we're kind of exploring all these little side paths on the way. Now we get right here. Here's another choice. Well, let's try going to the left. Okay, that dead ends. Let's go back. Let's try going straight. And here's another point. If we go straight, that dead ends. If we go right, that dead ends. We've run out of options from the choice that we made way back here. So going straight didn't work, so let's try going down this way. And if we follow a path and we eventually get to a dead end, we back up one spot and we say, okay, let's go back to my previous decision and try something different. So if we were to do this in a program, what we might do is each time we come to a decision point, let's say right here is decision point A, we might say, okay, I could go straight or I could go left, right? So we would want to remember both of those choices. We could say we could go straight or we could go left, and we might, you know, try to record those somewhere. And we could do this with a stack, right? We could remember that we were going to try to go straight, but we were also going to try to go left. So we'll push the straight onto the stack and we'll proceed to the left. And as we go around, maybe we'll come to a spot over here where we can either go straight or right. So we'll try going straight, but we'll remember, hey, if straight doesn't work, we could come back here and go right. And then we'll come around, we'll come to another spot, and maybe here we can choose to go left or right. So I'll remember the left option, but instead I'll go right. And I go to the right and I hit a dead end. What do? I come back, I pop this off the stack, I go back to this point and I say, okay, let's try going left instead. And if I eventually hit a dead end there, I will come back to this previous decision point and say, oh, maybe I should have gone right there. So I'll pop off the right and try doing a path from there. And as I do that, I'll make other choices, and each time I have choices, I'll put the other options on my stack. And eventually I may get through a whole bunch of paths and find out, you know, every way I go is a dead end. Okay, so maybe that first turn I made, I should have gone straight. So we'll pop that off and we'll start going straight and continue adding options to our stack. And so we can write a program that will solve a maze pretty easily, right? Basically, we need to keep track of where we are in the maze, and each point that we have where there's 2 or more options, we will choose one option. We can choose it at random if we want, or we could choose an order in which we take the options. And all the options we haven't taken, we're going to push those on the stack. We're going to record the location and the direction that we haven't traveled yet. And anytime that we hit a dead end, we're just going to pop the top of the stack. That'll be the last decision point we made, and we'll try a different path. And so if we do that, we'll eventually find a solution to the maze. Of course, the real trick, though, if you want to solve a maze, start at the exit, and most mazes are much easier to solve in reverse. So if you want to cheat, you know, you can start at the finish point and trace your way backwards and probably find your solution like that. But as a programmatic way, right, this is how we can use a stack to solve a maze. But we could also do this with a queue, right? We could say, let's go through our maze. Okay, should I go left or right? Well, I'll try going this way first. And then we come down here, and here's another decision point. Should we go straight or this way? Let's try going straight. So we'll come down here, and we'll come around, and here's another decision point. We'll try going left, and that hit a dead end. Okay, instead of going back and now taking our last decision and going a different way, we could go all the way back to the beginning and say, okay, so our first choice, let's try going straight instead of going left. That's not how most of us would solve a maze, right? We usually go back to the last place that we made a choice and make a different choice. But we could go all the way back to the first choice we made and make a different choice. That's going to be a breadth first traversal. And we could draw a binary tree to correspond to how we're traveling through this maze. It wouldn't be binary. It could be a 3-way tree if we had 3 choices to make. We could make a tree that represents how we're traveling through this maze. And at each point, when we make a decision, we have multiple branches coming out. Each branch corresponds to a direction in which we could travel. And then maze running is just a matter of traversing that tree. And we can traverse it depth first by moving down and then popping up just a little and going down a different branch. Or we could do breadth first, where we try to move across and slowly get deeper in the tree. But as long as you have a way to traverse that tree, you will eventually visit every node, which means you will have followed every possible set of decisions, and one of those should get you to the exit point. Alright, so we can also use the idea of depth first traversal to solve other problems. So let me give you an example, something called the n queens problem. And so imagine you have a chessboard. Like this. And a queen is a piece that wherever it's sitting, it can move any amount of squares forward, backward, left, right, or diagonally in either diagonal direction, as long as it doesn't hit another piece. If it hits a piece of its own color, it can't move beyond it. But if there's a piece of a different color sitting there, it can actually capture it. So queens can move, you know, any number of squares in any direction. This is what the queen actually looks like, right? So it's a super powerful piece. So there's a problem called the n queens question. So here we have an 8x8 board, and let's just pretend that these pawns are queens. And the question is, can we arrange 8 of these in such a way that none of them are attacking anyone else? I think I have one stuck under here. So I could put one queen here. The second queen can't go here because they're attacking each other. It can't go here because you can attack diagonally, but it could go here. And then the third one could go here, and the fourth one here. And then the fifth one, that could go here. That's safe. And the sixth one could go here. And the seventh one could go there. But the eighth one, there's nowhere for it to go. I have a queen in every row. And so this is the only row that's not under attack. And if I put a queen there, it's actually threatening that queen in that corner. I know you can't see these very well, but they're there. So the question is it possible to place 8 queens here so that none of them are attacking each other? And if so, how do you do that? And how many ways can you do that? And what if you had a 9x9 board with 9 queens? Or a 20x20 board with 20 queens? And this is a search problem. We'll talk about search problems separately in a few weeks and look at sorting and searching algorithms. But this is really just a glorified search problem. And so we can think of it as follows. How many different places can we place this first queen? Well, theoretically, there's 64 places. We could put it anywhere we want. And how many places could we put the second queen? Well, there's 63 places. We can't put it in that same square. And how many places could we put this one? There's 62 places. And so there's about 64 to the 8th possible places we could put these 8 queens. Well, that's a big number. We don't want to try each of those and check to see if it's a solution or not. But we could make this problem a little easier to do by saying, okay, we know that we're going to have one queen in each of these columns, each of these files. And so there's really only 8 places we could put this first queen, one of these 8 squares. And then the second queen, there's only 8 places to put it. And the third queen, there's only 8 places to put it, and so on. So there's 8 to the 8th possible ways we could place these 8 queens. And in fact, since we know that we can only have one queen per row, there's 8 places to put this queen. There's really only 7 places to put the second queen. And then there's only 6 places, 1, 2, 3, 4, 5, 6, to put the third queen, and so on. So it's actually 8 factorial possibilities just by using a little bit of knowledge about how queens can attack each other. And 8 factorial is not a huge number. So how would we code this? Well, we could think of this as a binary tree, right? We could think of this as make a node for our first queen. And there's 8 possible places we could place it. And for each of the places we can place this first queen, there's, 7 or 8 places we could place the second queen. And for each of those, there's 8 places, or 7 or 6, that we could place the next queen. So we could think of this problem as an 8-way tree. And we simply need to traverse this tree and examine all of the possible nodes. And one of these nodes will hopefully correspond to a situation where each queen has been placed in a way that it's not attacking any other queens. So this is a search problem. It's a traversal problem. We're taking this abstract problem of placing 8 queens on a board, and we're translating it into the construction of an 8-way tree. And then to search that tree, we simply need to traverse it. We need to visit every possible node, which corresponds to every possible way of moving from one level to the next, and try to find one of those traversals that, does not have a queen attacking another queen. And so we can do this with a stack. And the way we would code this as a stack would be something like, you need a way to represent the board, represent the position of each piece. But we could say something like, okay, let's look at the first queen, and there's 8 different places we could place it. We could place it on any of these 8 rows. And so let's push all 8 of those onto a stack. So let me push down these 8 positions. So this is column H, and it's positions 1 through 8. So H1, H2, H3, H4, H5, H6, H7, H8. So I'll push these on a stack. And that's it. If there's a solution, it will begin with one of these options, placing our first queen on one of these 8 squares. Alright, so I'm going to pop off one of these. I'm going to pop off H8. And H8 is going to say, hey, I'm placing my queen on this square H8. And now I can say, hey, let's solve the 7 queen problem. Let's find a way to place 7 queens on this 7x7 board so that none of them are attacking each other, and also they're not being attacked by this queen. Well, the only thing this queen does is it takes out this diagonal, but it can't attack any rows or columns in this. So now I recursively call my n queen solver, and I say, hey, find me a solution to the 7 queen problem in this area, and don't allow any pieces to be on this diagonal. And how do we do the 7 queen solver? Well, we would put down the positions of the initial queen in this 7x7 area, so G1 through G7, right? So we pop this off the stack. So now we can push G1, G2, G3, G4 through G7. And we would say, okay, let's try putting our queen at G7, and now we would solve a 6 queen problem. Alright, if we do all of that and there is no solution to the 6 queen problem, we would come back and we would say, hey, okay, let's try putting our first queen at G6. And we would try to solve the 6 queen problem that resulted. And if that didn't work, we'd come back and we'd say, okay, let's try putting the first queen at G5. And maybe we come through all of this and we haven't found a solution. What does that mean? It means that putting our first queen at H8 did not yield a solution. So now we come back to the original 8 queen problem and we say, okay, let's start off by putting our first queen on H7. So we put our queen right here. And now we would solve the 6 queen problem. And so we would push G1, G2, all the way up to G6 and G8. And of course, to solve each of these, we're going to make recursive calls to the 6 queen problem solver, the 5 queen, the 4 queen, and so on and so forth. So we could write this recursively, and it's really just a recursive way to travel through this search tree, which is enumerating the possible placements of 8 queens on an 8x8 board. And remember, we always need a base case. Well, what's our base case? 1 queen. If we have a 1x1 board and we have a single queen, let's say that's our entire board is H1, we have 1 queen, well, we just put our queen there and we've solved the 1 queen problem. We have one queen and it's not attacking any other queens on the board. So the base case is trivial. And then we build up from there and we try to solve the two-queen problem. Two-queen problem is not actually solvable, right? Because if you've got a 2x2 board, right, we can't put two queens on a 2x2 board and not have them attack each other. But the three-queen problem, I don't think three queens is solvable either, but four queens is. All right, so that's an example of another way that we can use this recursive idea, this idea of solving a problem by breaking it into smaller problems, solving those smaller problems, and then putting those solutions together to get a solution of the bigger problem. This, by the way, would be the solution to the four-queen problem, and I'm using white on the black square so you can see it more easily. But in this case, you know, each queen is sitting in its own square and it can't attack anybody horizontally, vertically, or diagonally. So there's a solution for the four-queen problem, and we could use that to find a solution for the five-queen and build up from there. The solution to this, if we actually look at it in code, we can write a solve function, which, you know, the hardest part of dealing with this in C is just the weirdness around expressing arrays and accessing elements of arrays and so on. But as far as the algorithm itself, this is the number of columns in the board, right? So the size of the board. This is how many have been completed, and this is how many we're trying to do. So if we've completed all the rows that we wanted to do, we're done, we print out the solution. Otherwise, we basically try putting it in each row, putting our next queen in each row that's available, and if that's a legal move, then we record it and we solve the simpler problem where we've done one more row or column, and we have the same total to do and the same column information that we've updated, right? And this is the whole solver, right? Everything else is just logistics for managing, you know, the way that C deals with arrays. But you know, this is it. Just try to place your queen in each row, and for each one, if it's a safe move, then solve the simpler problem where we've already, you know, done plus one queens, and the recursion handles everything else. So we can also use this for solving sudoku, where we have, you know, typically a board like this, and then each of these is broken into 9 squares, and you have a few numbers scattered around here, and we're trying to solve the question, you know, how do we fill in numbers in each of these squares so that each of these 3x3 boxes has each number once, and each number occurs only once in each row and each column. And it's just a search problem, right? There's a lot of work to do, but the work itself is pretty straightforward. We could simply try all possible combinations, right? We could try putting a 1 in here, and a 1 here, and a 1 here, and fill in every square with a 1. Well, that's not going to work. So you could back up one step and change our last square to a 2. Well, that's not going to work. Back up and try changing our last square to a 3. When we run out, back up an extra step and change a second to the last square from a 1 to a 2, right? And we can eventually get through all the possible combinations. But rather than taking that brute force approach, what we can do is we can, you know, make this a recursive solver and say, okay, I'm going to plug in a 1 here. If that's a legal solution so far, now just call my solver on this slightly easier problem where I've already filled in 1 square. If it can solve that problem, then I've solved my original problem by putting a 1 in that first open spot. If not, I can put a 2 in that first spot if it's legal. Well, it's not, so I could put a 3 in that spot and then try to solve the resulting problem. And if it finds a solution, I've solved the original problem by putting a 3 in there. And this is again pretty straightforward to code recursively. And the code looks very similar to how we do n queens. A lot of legwork, you know, function prototypes, reading in a board from a file, printing the board, making it look pretty, and so on and so forth. But the actual solver, relatively short. So how do we solve? Well, we go through each row and column, and if that spot's already filled in with a number, we don't touch it. But if the spot is open, we try all 9 possible numbers. So we tentatively set the board entry to our next number that we're going to try and see if it's legal. If it's legal, then we call our solver. This is the solve board function. We call the solver on the remaining board. And if it's not legal, then we skip that solution. And then when we're done with that iteration, we mark that square empty again by filling in a 0 there. And that's all there is. This will solve our puzzles for us. So if I want to solve the n queens problem for 4x4, it actually comes up with 2 solutions for that. So one solution is to go into rows 2, 4, 1, and 3. And so that would look like this. And let me use some different colored pieces here. So this would be 2, and then 4, and then 1, and then 3, and that's a solution. And the other solution is 3, 4, 1, 2. So 3, 4, 1. Sorry, 3, 1, 4, and 2, and that's the solution. And if you want to solve this for the 8x8, there's a bunch of solutions. There's 92 solutions. And we could just pick off this last one. And so this says we should go in 8, and then 4, and then 1, and then 3, and then 6, 2, 7, 5. And again, I'm just using different colors to make it easier to see. But that should be a good solution. No queen is in the same row or column as any other. And if you inspect the diagonals, they should all be safe from attack. So there's our solution for 8 queens. On the 9x9 problem solver, which I can never pronounce, sudoku, I don't know. So here's a sample problem. So space 9, space 2, space 5, right? So this is how the squares are filled in normally, and we've got, you know, a lot of numbers squared in. So if I run my solver and redirect that in, here's the solution it comes up with. Right, so the original formulation said there was a 9 in the middle of the first box, and a 2 in the middle of the second, and a 5 in the middle of the third, and then a 2, 1, 8 in the beginning of the second row, and so on. And so here's a solution. And it took 162 calls to solve. So there were 162 nodes in our search tree. Here's a more complex one. It doesn't have quite as many numbers filled in, and that took 216 calls to solve. Here's one with very few numbers, right? Most of these are missing spaces. And so there's more options because we have fewer numbers to cause a move to be illegal. But it can solve that quickly, but it took almost 26,000 recursive calls to come up with a solution. But that's a good solution. So this is a powerful technique. It's generally applicable to search problems, right? So that's an important application of depth first search. So let me wrap this up by looking at 2 particular applications to tree traversal. We already know how to do tree traversal recursively, but we can also do it iteratively by using stacks and queues. So let me give you an algorithm for traversing a tree in order using a stack without any recursion. So this is going to look like the following. So the first thing we do is we push the root onto the stack. So our stack has to store not just numbers, but it's got to store nodes so that we can get to, children of the things we push and so on. And I'm going to write this with some labels. So we'll have some go-tos in here. We can pretend it's assembly language. So what does our main loop do? It says move left and push. And we'll keep doing this until you can't move left anymore. So that's our main loop, and then we're going to hit a sub loop L2, which says pop from the stack, print whatever value we popped, and then if right child exists, push and go back to loop. So come back up here. Otherwise, go to L2. So come back up here. So there's no recursion in here. This is a function called left node right that's supposed to traverse our tree in order. And it's purely iterative. Start off by pushing the root and then move left and push nodes as far as you can until you can't move left any further. Pop the last thing you pushed, print it out. If there's a right child, push it and go back here. Otherwise, pop, go back up here, pop what's at the top of the stack, print it out, and continue. And so if we have a tree that looks something like this, what would this do? Well, let's make a picture of our stack. And I'll grow my stack in this direction. So this will be like a stack of dishes. I'll just start putting my numbers down here at the bottom and writing them up, going up to the top. Okay, so how do we seed the process? We start off by pushing the root. That's a 20. And let me record our output here to see if this actually does left node right traversal. So we start off, we push the root onto the stack. Now we get to loop, and it says move left and push. So we're going to go to the left. There's a 10, we'll push that. We'll move left, there's a 5, we'll push that, until you can't move left any further, so we're stuck. So now we say pop the top of the stack. So we pop off the 5 and we print it. Alright, we popped off the 5. If the 5 had a right child, we would push it and go back up to loop, but there's nothing to the right of 5. So we go back to L2, which says pop the top of the stack. So that pops off the 10 and we print it. And so we popped off the 10. If there's a right child, push that on the stack and go back to loop. Well, 10 does have a right child, which is 12. So we'll push a 12 onto the stack and we go back to the loop. And 12 says move left until you can't move left any further. Well, we can't move to the left of 12. So we come to L2, which says pop that and print it. And if 12 had a right child, we would push it and go to loop, but it doesn't, so we go back to L2. And L2 says pop the top of the stack, which is now a 20, and print it. And then if 20 has a right child, well, it does, push that onto the stack. So now we push a 30 on the stack, and we go back to loop. Move left and push until you can't move anymore. Well, we can't move to the left of 30, so we come to L2, we pop it, we print it. And then if there's a right child, which there is, we push it. So push a 40 on the stack. I'm just moving up here because there's more space. Push a 40, go back to loop. Loop says move left and push, so there's a 35, so we'll push that on the stack. And go back and try to move left. We can't go to the left of 35 anymore, So go to L2, pop the 35, print it, and then try to move to the right. Well, there's nothing to the right of 35, so we can't do that. So we go back to L2, which says pop the top of the stack. And then if you can move to the right, push it on the stack and go to loop. Well, 40 has a right child, which is 50. So we push 50 on the stack, we go back to loop. Loop says move to the left. There's nothing to the left, so we can't do that. So we pop the top of the stack. That's a 50, and we print it. And if there was a right child, we would push it, but there's not. So we go back to the top of the loop, which says move left as far as you can. Well, there's nothing to the left to move to, so this says pop the top of the stack, and the stack is empty. So if empty, then we're done. And in this case, right, the stack's empty, so that's the end of our algorithm, and we've printed out the entire tree in left node right order. Oh, and a small misstep in that last example we went through. After we popped the 50, we should have discovered there was nothing to the right, and so we went back to L2. That's when we tried to pop from our empty stack. Found it was empty, and so we were done. So we don't actually go back to loop because there was nothing to the right of 50. So you can see, if you study this, what's happening, right? Each time that, so we start off by moving as far to the left as possible, right? That's what the L is. And when we can't move any further, the last node that we pushed will be the leftmost node. We pop it and print it. So that's the node part. And then we should traverse to the right. So if there's a right child, we push that onto the stack and we come back up here to the top. Well, that means that entire right subtree is going to be traversed in an LNR order. And when that's all done, then we'll come back and we'll move up one more level. So this is depth first, right? So that gives you the same behavior as doing our recursive left node right. And as usual, recursion, stack, right? Stacks basically mean recursion. But we could do something very different. So let me copy this tree. 20, 10, 5, 12, 30, 40, 35, 50. And let's instead do a breadth first traversal. And so this algorithm is going to work as follows. All right, so breadth first search. How does this work? This one's a lot easier to describe and to understand. So we start off by pushing, by inserting root into our queue, and then we just have a loop. So while the queue is not empty, we remove the head of the queue, we print it, and then we insert its children into the queue. So it's a simple iterative algorithm. We seed it by inserting the root into the queue, and then as long as the queue is not empty, we do the following: remove the head of the queue, print out its value, and then insert its children into the queue. So here's what our queue looks like. And here's what the output is. So we seed the process by inserting the 20. And then in our while loop, we say the queue is not empty, so remove the 20 and print it. And then insert its children. So we'll put in a 10, and we'll put in a 30. And let's suppose, this is the head, and this is the tail. So we're inserting things in this way. So we put in the 10 and the 30. Then we go back to the top of our loop, remove the head of the queue and print it, so that's a 10. And then insert the children of 10, so we put in a 5 and a 12. Go back to the top of the loop, remove the head of the queue as a 30, print it, and insert its children. Well, it has no child on the left, but it has a 40 on the right, so we insert that. Remove the head of the Q, that's a 5, print it. Insert its children, well, it has no left or right children, so nothing to insert. Remove the head of the Q and print it, that's a 12. It has no children to insert. Remove the head of the Q, this is the last thing in the Q, is a 40, print it. Insert its children, so there's a 35 and a 50. Remove the head of the Q and print it, that's our 35. It has no children to insert. Remove the head of the Q is 50, print it, insert its children. It has no children to insert. Remove the head of the Q, but at this point, right, when we come back up, we find the Q is empty, and so our traversal algorithm exits, and we're done. And what's the order in which our nodes were printed? Well, first we printed the 20. That's this node right here. Then we printed the 10 and the 30. Those are the levels one step deeper. Then we printed 5, 12, and 40. Those are the nodes one step deeper. And then we printed 35 and 50. Those are the ones even deeper. So this is breadth first. We start off at the shallowest node, and we print it, and then we go down just one more level and we print everything at that level. We go all the way across the breadth of the tree at that depth, and then we go one step deeper and print everything at that depth and keep going. So we're moving across most quickly and slowly going down. And it's the counterpart to depth first, where we move down and print all the stuff at these deeper levels and slowly work our way up. So that's a different way to print a tree, and in this case our nodes are not sorted numerically, but they're in some sense arranged by depth. And so if we were to look at the tree ourselves and someone asked us, you know, tell me all the numbers in the tree, we might do something like this. We might just scan from left to right and slowly go down. It's a very natural thing for humans to do. So that's a different way to travel through the nodes of the tree. So that's breadth first. All right, so that's just an example of stacks versus queues, depth versus breadth, ways that we can solve different algorithms, that we can do basically search problems by examining a space of possible solutions and looking for a particular solution. All right, thanks.